Hi everyone. In today's video we're going to build off what you did in today's Desmos activity and talk a little more specifically about the details of the concept of continuity. So for our purpose, when we're talking about a function being continuous, what we really mean is that it's connected. So in other words, if a function's continuous, it means I could trace along that function and I wouldn't ever have to lift my pen. So I shouldn't have any holes or asymptotes or jumps. So that's kind of the intuitive definition, is this idea of a connected function. Now, as we get deeper into this, what we're going to start doing is relating this to limits. And we're going to have a limit definition for continuity. And here's what that definition is going to look like. In order for a function to be continuous, we're going to say that the limit, and we're going to talk about continuity at a point. So for in order to be continuous at a point A, we said that the limit as x approaches a from the left of f of x has to be equal to the limit as x approaches a from the right of f of x, right? So we're saying right there that the two-sided limit exists. And now for it to be continuous, that limit also has to be equal to the function value. And we're going to be coming back to that limit definition quite a bit. Now, not every function is going to be continuous. So our first example was continuous. Our second is not. So if a function has a place where it's not continuous, we say it has a discontinuity at that point. So, for example, if I'm tracing along this curve, I realize that when I get to the point x of 0, I have to jump to pick up the next piece of that function. So this function has a discontinuity at x equals x of 0 because of that jump. Now, assuming this goes off here and here, we can say it is continuous for x values from negative infinity to x of 0. And I'm going to leave that open here because I know it's discontinuous at x of 0. And then I'm continuous again from x of 0 to infinity. So I have a discontinuity at this point, but on all the intervals on either side of that point, I'm continuous. Now, we're going to have 4 specific types of discontinuities. And let me adjust here so you can see this. Okay, we have 4 specific types of discontinuities. Okay, the first is called a jump discontinuity, and this will happen likely when you have piecewise functions. Now, if you think back to that limit definition that we talked about, right, we said for it to be continuous at a point, the two-sided limit had to exist and it had to be equal to the function value at this point. So if we think of why this is not continuous, and it looks like at C here, we know it's not continuous because the limit as x approaches c from the left is not equal to the limit as x approaches c from the right. So as soon as we fail kind of that first condition, we know that we're not discontinuous. So if we were asked to explain why it's not continuous at c, we would say the limit as x approaches c from the left of f of x is not equal to the limit as x approaches c from the right of f of x. Now, the next one is an infinite discontinuity, right? And these happen because we have a vertical asymptote here, right? Which we could see with a rational function. Now, in terms of our limit definition, we can see actually, let's see, this looks like it's at the x value of 2 here. We can see that the limit as x approaches 2 from the left and x approaches 2 from the right are the same value. So we actually do have a two-sided limit. This two-sided limit exists But because f of 2 is not defined, that two-sided limit doesn't equal the function value at 2. And that's why that function fails the limit definition for continuity. All right, the next one is called a removable discontinuity. This is where we would have a hole. And again, this is likely going to occur with a rational function. Now, much like we saw with the infinite discontinuity, in this case, as I approach C from the left and the right, I'm approaching the same value. So the limit, the two-sided limit, does exist. However, f of C is a different value from that limit, so the two-sided limit isn't equal to the function value. So the last type of discontinuity we have is an oscillating discontinuity, and this is going to occur with trig functions. And what's happening here, it looks like we would say this is discontinuous at x equals 0. What's happening here is these functions are jumping back and forth between these kind of the high point and the low point so fast, and they're never converging on a single value. So in this case, we would say we can't actually define a two-sided limit. We would say the limit as x approaches 0 from the left of f of x is not equal to the limit as x approaches 0 from the right of f of x. So those are our 4 types of discontinuities that we'll keep coming back to as we go through the notes and through the chapter. All right, so moving on. We're going to go through a couple of examples here. The first thing we're going to do, and I'm going to adjust my paper again here. First thing is we're going to locate and classify the discontinuities of the graphs. So we're going to find where it is, the type, and why it fails that limit definition of continuity. And then we'll find the intervals where our function is continuous. So as I'm going from left to right, the first place I notice a discontinuity is at x equals -1. And I would classify that as a jump. Now, we know with the jump, the problem here is that the limit as x approaches -1 from the left of f of x, we know that's 3, which is not equal to the limit as x approaches -1 from the right of f of x, which has a value that looks like just a little less than 1. So that's our first discontinuity. Now, the next one I'm noticing is at x equals 0. It looks like there's an asymptote here. If I look from the left, this value looks like it's going to positive infinity. So I have an asymptote there. So I would classify this as an infinite discontinuity. And again, in terms of limits, we have the same issue where the limit as x approaches 0 from the left of f of x is not equal to the limit as x approaches 0 from the right. Okay, now the last place I have a problem is here at x equals 1. Now, in this case, we call this a removable discontinuity. And the reason it's called that is because I could fix this discontinuity if I could just assign the function value to this point. So I can literally kind of fix it by plugging in that hole. So in this case, we do have a two-sided limit. I know the limit as I approach from both the left and the right would be 1. So the two-sided limit exists. However, it is not equal to the function value at that point. So in terms of the intervals of continuity, the first interval I have is what I'm going to trace here in red. So I'd say I'm continuous from -infinity. Now, at -1, my function is defined at that value, so I'm going to put a closed bracket there. Now, my next interval is going to be from here to here. So from -1, now I'm open here because I have an open circle, and I'm going to be open at 0 because I'm approaching 0, but I never actually equal 0 there. My next one is going to be in between here, and again, because I'm open circle on either side, I'm going to have open brackets between 0 and 1. And then my last interval will be this place here, or this piece, from 1 and then to positive infinity. So I have 4 intervals of continuity. All right, so we're going to do one more example. Again, it's very similar, so it might actually be a good idea for you to pause the video at this point and go ahead and try this problem on your own. So if you'd like to do that, go ahead. All right, so in terms of discontinuities, as I'm working my way from left to right, the first issue I see is that x equals -3, and that's going to be, again, our jump discontinuity. And our issue here is that the limit as x approaches -3 from the left is not equal to the limit as x approaches -3 from the right of f of x. The next place I have an issue, I can see I have a vertical asymptote here at x equals -1. It kind of looks like it's connected, but because I know I have this asymptote here, we're going to treat that as an infinite discontinuity at -1. Now, in this case, again, my two-sided limit exists because from either side of -1, I'm approaching positive infinity. However, f of 1 is not defined, so that limit as x approaches -1 is not equal to the function value at 1. And then moving on, I see at x equals 2, I have another removable discontinuity. And again, my two-sided limit at 2 exists. I can see by looking at the graph that that limit is -0.5, but the actual function value is -1, so that is not equal to f of 2. So again, we're going to have 3 intervals of continuity. My first piece will be from -infinity to -3. My second interval is going to be from -3, and I have a closed bracket here because my function is defined there. And it'll be up to -1 where I have that asymptote. So -3 to -1, I'll be open. Then I have from the other side of my asymptote at -1, I'm continuous all the way until x equals 2. And then my last interval is from 2 to infinity. All right, so that's what you need to know about continuity at this point. Again, just like limits, we're starting with analyzing it graphically, and then we'll be able to move into a more algebraic approach to continuity. So thanks for hanging in there, and I will see you in class.